Alright folks, welcome back to Moonshine Radio. Today we're going to take a look at some of the digital IQ sampling methods that are out there, and towards the end we will cover something called IF subsampling, a an idea that's kind of showing Nyquist and other trickery that you can do. But first we will show the classical method of how the red pitaya 125 works for receive. You have an input signal. It goes through a low pass filter, 0 to 60 megahertz, then goes to an analog digital converter running at a 125 megahertz clock. So classically, that's why we have the 60 megahertz low pass in front of the ADC to prevent alias signals from getting sampled. So this is your classical setup. And then after the analog to digital converter, in the firmware they have what's called a DDC block, digital down converter, and which converts the high sample data to a lower sample IQ stream centered at some frequency that you can tune around. So in this case, you could tell the DDC to tune somewhere around 0 to 60 megahertz. And in this example, we're showing it will have a final IQ bandwidth of 50 kilohertz. So this is a classical definition of what's going on in your red pitaya unit on the receive side. So let's go through an example of how we would use that for a signal. Let's say we have a 455 kilohertz IF signal out of some old radio, and we want to digitize it and get it into SDR software. So if we were to use the red pitaya, basically you would just put the 455 kilohertz signal through. It would get sampled by the analog digital converter at a 125 megahertz rate. It would then go into a DDC block in which we would tell the frequency tune to be 455 kilohertz. And after that, we would then decimate down such that our final IQ sample rate would be 50 kilohertz. But if we think about that, that seems to be a lot of processing. We have a 455 kilohertz signal. In this case, let's say it's band limited by 10 kilohertz. And then we're sampling that with a massive 125 megahertz data rate. All that just to finally reduce it to a lower sample rate. So that's a lot of processing on the firmware just to get some small bandwidth. And our question today is, could we come up with a scheme that uses a much lower sample rate than 125 megahertz? And that's what is typically called IF subsampling. So the picture I show now is one method of how you could do that. We have the 455 kilohertz signal. In this case, it's now going through a bandpass filter to guarantee that we only are going to have a 10 kilohertz bandwidth centered at 455 kilohertz. We can then send that through an analog to digital converter, now running at a 400 kilohertz sample rate, much less than the 125, so a lot less power, a lot less energy. And then after that, we can feed that into a digital down converter, in which we would tell the frequency tune to be 55 kilohertz. Now, why is that? Because after that A to D, that 455 kilohertz signal is going to show up at 55 kilohertz. It's essentially going to alias down to 55 kilohertz. And since we want the 55 kilohertz to be centered at DC, that is why we tell the digital down converter frequency tune to be 55 kilohertz. A little trickery there, but if you go through it, you will realize that that is indeed correct. And why can we do that? Well, it's getting back to what's called Nyquist zones. So 400 kilohertz is our clock. We have 0, 400 kilohertz, 2FS, all the way up. And we can see that 455 kilohertz is essentially 55 kilohertz above our sample rate. So what that means is that the 455 kilohertz signal will alias down to 55 kilohertz. So you can see that is why the bandpass filter is needed to ensure that there will be no signal anywhere below 455 kilohertz, because it will also show up in those zones, and we don't want that. So long as we have a bandpass filter in front of this analog to digital converter, we can do this. And this technique is what's called IF subsampling. We are sampling an IF signal at a much lower sample rate. And because our signal is band limited, we can get around this. So this is often not talked about, but it's heavily used in industry. And it makes sense because now this analog to digital converter is running at a much lower clock, a lot less heat and power consumption. And at the end of the day, we're still getting the same 55 kilohertz sample rate for further processing. So, quick video today on Nyquist zones, digital down converters, and IF subsampling. Now, if you're not sure what a digital down converter is, go see my video where I detail that in much more depth than I did today. But that is a very important block that's used in our modern DSP SDR world. So I hope you learned something today on digital down converters and IF subsampling. Live from Moonshine Radio University, this is Moonshine Radio.